Good morning. Good morning, everyone. And welcome to our plenary talk, the second plenary talk in this conference. It's a pleasure and an honor for me to introduce our plenary speaker for today, Professor Daniel Spielman from Yale University. Daniel has made groundbreaking contributions in theoretical computer science. His work has been very influential in many scientific and technological areas, including ours. In describing Daniel's scientific achievements, I'll try to be brief, but it's not going to be easy. Daniel Spielman received his PhD in applied mathematics in 1995 from MIT under the supervision of Professor Michael Sipser. The title of his dissertation was Computationally Efficient Error-Correcting Codes and Holographic Codes. His dissertation received the 1995 ACM Doctoral Dissertation Award. He received the 2002 IEEE IT Best Paper Award together with Michael Luby, Michael Mitzenmacher, and Amin Shokrolahi for the paper Improved Low-Density Parity Check Codes Using Irregular Graphs. In 2008, he was awarded the Gödel Prize for his joint work with Shang-Hua Teng, Smooth Analysis of Algorithms, Why the Simplex Algorithm Usually Takes Polynomial Time. In 2010, Daniel received the Navanlina Prize, awarded once every 4 years to outstanding contributions in mathematical aspects of information sciences. Like the Fields Medal, it is targeted at young mathematicians under 40 at the award year. He was cited for smooth analysis of linear programming algorithms for graph-based codes and applications of graph theory to numerical computing. In 2013, in a joint work with his postdoc Adam Marcus and student Nikhil Srivastava, he provided a positive solution to the Caddison-Singer problem, a work that was awarded the 2014 George Polya Prize, given every even year for specific works or contributions. In 2015, Daniel Spielman and Shang-Hua Teng received for the second time the Gödel Prize for a series of papers they co-authored on nearly linear time Laplacian solvers. This work resolved an open problem in numerical linear algebra, solving symmetric diagonally dominant linear systems in nearly linear time. The impact of these papers has extended far beyond the results. It has been used to obtain substantial asymptotic improvements in the running time for several core problems in graph theory. And I guess that the talk we are going to hear today is related to this line of works. So without any further delay, let me give the stage to Daniel.
Let's see here. Good. So my goal for today is to tell you a little bit about the Laplacian matrices of graphs and the things we can do with them. And in about 30 minutes, I'll explain that picture. So I'm going to begin my talk, rather than really by defining Laplacians, by motivating them. I'll try to do that by telling you about a lot of the applications in which they appear. So I'll tell you about things like problems in interpolation on graph clustering, and some of the physical metaphors for graphs that enable us to analyze, like thinking of graphs as spring networks or thinking of graphs as networks of resistors. Then I'm going to tell you a little bit about some of the interesting things we can use Laplacians to do, like, for example, define a notion of what it means for one graph to approximate another. And once we have this definition, we can do something called sparsification. That is the approximation of an arbitrary graph by a sparse graph. And this will give us a way of making that formal. Now, a large part of the reason that I'm going to be talking about Laplacians is that we can compute with them efficiently. So I will, towards the end of the talk, tell you about some of the very fast algorithms for solving systems of linear equations in Laplacians, which we can also use for computing their eigenvalues and eigenvectors. And in particular, I'm going to finish by explaining to you a very, very recent paper that was just published a month ago by Sushant Sachdeva and Rasmus King, which gives really an amazingly simple algorithm for solving systems of linear equations and Laplacians in nearly linear time. OK, so there's a bit of an echo in here. Can I just get a show of hands for how many of you can hear me well? Good. OK, then I won't worry too much. But I'll try to talk in a way to reduce the echo. OK, so here's one motivating application of Laplacian matrices that comes from a paper of Drew, Garamani, and Lafferty from ICML in 2003. It considers a problem of interpolation on a graph. So you should imagine you have a graph in which you know something about some of the nodes, and you want to make inferences about the others. So for example, this is a part of a protein-protein interaction network. And imagine you're trying to figure out which proteins are active within a disease, like diabetes. And of course, determining this involves real lab work and experiments and takes a lot of time. So you can only do it for some of the proteins, at least efficiently. So imagine we've determined, say, that one of them, ANAPC10, is involved in diabetes, and another one, CDC27, let's say we've determined is not. Caveat, don't believe me that that's actually true, maybe. OK, so now you'd like to figure out which other proteins to study. So in a protein-protein interaction network, people have drawn edges between these proteins when they are known to interact. That is some measure of similarity. So we'd now like to estimate, given the knowledge that we have, what's the probability that these other proteins are involved within diabetes? So we want to assign some number to each of them that we think of as that probability. And we want those numbers not to vary too much across the edges, because we believe that edges indicate similarity. So Drew, Garamani, and Lafferty suggested doing this by assigning a number to every protein so as to minimize the sum over the edges of the difference of the squares of the values in the edges. This is the assignment that minimizes that. So this quantity that they are minimizing, the sum over edges of the squares of the difference of the function across the edges, is the Laplacian quadratic form. And we will use that to define the Laplacian matrix of a graph. It'll be the central object of study in this talk. I should just mention to fix notation, I use letters like A and B for vertices of the graph, and things like x I think of either as a vector indexed by the vertices or a function from the vertices to the reals. OK, so whenever you have a quadratic form like that, there is a symmetric matrix, L, so that you can write that term as x transpose Lx, where in this case, L is the Laplacian matrix of the graph. And for the beginning of the talk, this is how we are going to define the Laplacian. Now, it seems a little strange to define a matrix by giving it its quadratic form, and many of you would rather see the entries. But trust me, everything you want to know about the Laplacian really comes from this quadratic form. And and I'm trying to do you a favor. When I was first taught about Laplacians, people told me what the entries were and then gave me homework problems to prove all sorts of things about them. And all of those homework problems were trivial if you realized this was the quadratic form. So this is really what you want to work with. OK, if you wanted to perform this minimization, you see that it's a quadratic. You could take derivatives. And then you realize that what you need to do is solve a system of linear equations. And that corresponds to solving a system of linear equations either in the Laplacian or, properly speaking, a submatrix of the Laplacian. But principal submatrices of Laplacians are basically like Laplacians. So we won't have to worry about the difference. OK, so just to emphasize once more, the principal object in this talk is the Laplacian quadratic form of a graph. So it takes as input a function from the vectors to the reals and returns to you a measure of how smooth that function is over the graph. So it's the sum of the difference across the squares of the differences across edges. So for example, here's our function x. And theirs are the squares of the differences across the edges. And you add them up, you get the Laplacian quadratic form. We can also naturally deal with weighted graphs as long as the weights are non-negative, or let's say positive. So you can have a positive weight on every edge. And then the natural thing to do is just multiply the corresponding term in the quadratic form by that weight. OK, now, Laplacian matrices of graphs have been studied for a very, very long time. Essentially, the first application I'm aware of is in modeling networks of resistors. So if you haven't, and by the way, I personally am not that excited about networks of resistors, except to the fact that they let me think about graphs. So if I have a graph, I think of each edge as a resistor. if I have a weight on the edge, I should be clear, the weight is the reciprocal of the resistance. Because for me, a very, very high weight edge is a very strong connection, which means, of course, zero resistance or very small resistance. So one of the things you can do if you have a network of resistors and you want to understand them is you can, say, attach some of the points in the network to the terminals of a battery. And then that will fix the voltage, say at 0 volts and 1 volt. And then physics tells us that the remaining voltages will minimize this Laplacian quadratic form. Again, I did this assuming all resistances were 1. Otherwise, I'd have to put the resistances in the quadratic form. OK, so these are the voltages that minimize the resistance. So this is really exactly the same thing that Drew, Garamani, and Lafferty were doing. The reason they're different numbers is this is a slightly different graph. This graph I drew to have cleaner numbers. OK, and of course, once you do this, you can take a look at what is the square of the difference across all of the edges. That's what the Laplacian quadratic form gives you. That tells you how much heat is being dissipated by the resistors. But more importantly, when you look at a network of resistors, there's current flowing. And that tells you something. So you can actually take a look using Ohm's law. Once you know the voltages at all the nodes, you can figure out how much current is flowing along every edge. And this then gives you a very useful measure of how related two vertices are in a graph. We define the effective resistance between two vertices in the graph to be, essentially, if you treat the entire network as one complex resistor, this tells you what is the resistance between them. Or if you want to define it by using Ohm's law, take a look at putting 1 volt of potential difference between the two nodes here. Take a look at how much current flows. The reciprocal of that would be the effective resistance between those two nodes in the graph. So one of the reasons that we like measuring this is because we want, we make graphs to measure connectivity. And of course, there's a natural notion that if nodes are actually right next to each other in a graph, then they are connected. But you want to extend that notion out. And you want to measure how well connected are nodes that are, say, further apart. And then how well connected they are should be something like the reciprocal of the effective resistance. In some sense, the effective resistance is low if there are many short paths between those nodes. And those paths should be different, of course. OK, so here's another physical model that gives us Laplacians, measuring spring networks. So in this case, a very natural thing to do with a graph is imagine that every single edge is a spring. In this case, I'll make them all have the same spring constant. And then you can do things like nail down the positions of some of the nodes and let the remaining ones settle. And the way the Laplacian comes up in this case is you recall that there's a notion of the potential energy in a spring, which should be the square of the length to which it has been stretched. And physics tells us that the position of the nodes when they settle will minimize the potential energy. So it'll minimize the Laplacian quadratic form of the positions, again, subject to your boundary constraints, which are the nails holding the vertices on the screen. OK, so here's the first place I know of people using spring networks to study graphs. It's in an amazing paper by Tut from 1963 called How to Draw a Graph. OK, so now I want to do a test to see how good a job I'm doing here. How many of you have seen this paper by Tut before? OK, then the rest of you are in for a real treat, because almost none of you have seen it. It's an amazing thing. So what he suggested doing was, let's say we have a graph, we want to draw it. In this case, he's talking about planar graphs. We don't know from this picture that this is planar, but if it were, you could find a face. So let's say a triangular face. Let's take the vertices in that triangle, move them to the outside of the picture. Then we will nail them down. And now let all of the other edges be springs and let them go. And they'll bounce around for a while. And eventually, this thing settles down. And when it settles down, you might notice you get a planar drawing of this graph. And Tut actually proves that if you have a planar graph and you have a face, and you nail down that face at the outside, and then you let the spring network settle where it should, there are no crossing edges in the picture. You actually get a planar drawing of the graph. And OK, it's a little, this picture, you can't quite tell it's planar because there are all those vertices jumbled up in the middle. Let me do it with a different face. You can take any face as long as you embed it at the corners of a convex polygon. So I can take this one, we can move it to the outside, nail down the vertices, let them bounce around, and we'll get a much better picture. OK, so this theorem is amazing to me for two reasons. First, because it's true. I mean, that's amazing, right? Springs don't know anything about my human desire to draw a graph with no crossing edges. Yet they do it if it's a planar graph. OK, that's already amazing. The other thing that's amazing is Tut proved this in 1963. So I know if I were going to prove a theorem like this, I would have done a million experiments on small examples to check that it were actually true before having the guts to go and prove something like this. I'm pretty sure Tut didn't have access to that sort of computational power, let alone a monitor to look at all of this. Let's see here. OK. So one of the other reasons that I study Laplacian matrices of graphs is because I'm interested in this field of spectral graph theory, which says, hey, when you have a matrix, you can look at its eigenvalues and eigenvectors. And it turns out that these tell you a lot about a graph. Now, that's not necessarily obvious, and I don't have time to make it obvious, but I have time to try to give you some intuition. So that's what I will do. So when I say these tell you a lot about a graph, I mean that in two senses. One, there are a lot of theorems you can prove relating structural properties of graphs to their eigenvalues and eigenvectors. There are also a lot of heuristic applications of eigenvalues and eigenvectors that are very useful. And I will show you one of them because that will help at least give you some intuition. But to begin, I need to tell you there's one eigenvector and eigenvalue that's not very useful. That's the smallest. If you look at the Laplacian matrix, it's actually singular. The all ones, it has a zero eigenvalue corresponding to the all ones eigenvector. OK, that doesn't tell us very much. Other than that one, they get interesting. So in particular, Hall in 1970 said we can use the eigenvectors of a Laplacian matrix of a graph to draw the graph. So Hall's idea was you take some graph that you don't really know how to draw, like this picture here doesn't tell me much about the structure of this graph. But I just drew an arbitrary picture of a graph. So what Hall said is let's compute the eigenvectors of the smallest eigenvalues of the Laplacian. So we'll compute, so lambda 1 was 0. We'll compute lambda 2 and lambda 3. We compute the corresponding eigenvectors. And then we use those eigenvectors as coordinates for the vertices, and we draw them there, and we get this picture. OK, so to emphasize, this beautiful picture of this graph, which really, once I see, I understand the structure of the graph, is drawn by using no geometric information. We just have the connectivity information. We compute two eigenvectors, v2 and v3, corresponding to the second smallest two eigenvalues. I use v2 as the x-coordinate here, v3 as the y-coordinate. That gives me a location for every vertex. And then we draw the edges as straight lines. And that gets me a very nice picture of this graph. So as a matter of fact, whenever someone comes into my office and says, Dan, I have a graph, can you tell me something about it? This is the first thing I try. Because it doesn't always work, but often when you can draw a graph this way, if you get a nice picture, it reveals a lot of the structure of a graph. So for example, here's a graph we'll draw this way. OK, the picture on the right is nice and geometric. This is the famous airfoil mesh. It was used for modeling airflow around a cross-section of an airplane wing. For those of you who are MATLAB users, if you're in MATLAB and you type load airfoil, you get this mesh. So it's just one of their standard default test cases. OK, so this has a nice picture. This picture on the right comes from the spectral drawing of the graph. Literally, we took every single vertex. We took v2, we computed v3, and plotted every single vertex according, with x-coordinate v2 and y-coordinate v3. And we get, again, a very nice picture of the graph. And if we zoom in on a section of it, you'll see it remains nice even as you zoom in. As a matter of fact, it is an almost planar drawing of this graph. It's not quite planar. But it is remarkably nice for a drawing that you're generating in, say, 3 lines of MATLAB code, only using the connectivity information of the graph. And of course, this won't get you a planar picture of every planar graph. So take the dodecahedron. If we take the skeleton of the dodecahedron, that is a planar graph. But we don't get a planar picture doing it this way, because the dodecahedron really belongs in 3 dimensions, not on 2 dimensions. And if we were to actually compute the first 3 eigenvectors of the dodecahedron, we'd get the perfect skeleton of it in 3-dimensional space right where it should be. Same for every Platonic solid. But if you only take 2 eigenvectors, you get what the dodecahedron projected down to the plane. I mean, actually, though, you really can't get 2 eigenvectors. Well, I mean, you can, but you're making an arbitrary choice when you do that. If you take a look at the one skeleton of the dodecahedron, the first eigenspace is multiplicity 3. So when you're choosing 2 eigenvectors, you are making an arbitrary choice of how you're going to project this down to the plane. Now, as I said, not all graphs can be drawn nicely this way. For example, we can take a look at the co-authorship network of Paul Erdős. So in this case, I took every paper that Paul Erdős wrote, made every single one of his co-authors a vertex, and put an edge between them if they were co-authors on a paper. OK, the graph was disconnected. I took the largest connected component, and I didn't bother to put Paul Erdős in it because he'd be connected to everyone. And that just gets silly to draw. But still, you don't get a very nice picture. I mean, that is because, right, some things can't be drawn. Now, I guess you can ask, am I just trying to make excuses, or can we actually prove some things can't be drawn well? You can prove it. As a matter of fact, this is one of my favorite homework problems to assign when I teach spectral graph theory. I tell the students something like, state formally and prove that if you can draw a nice picture of a graph, then it has a small value for lambda 2. And you can come up with all sorts of different ways of formalizing what it means to draw a nice picture of a graph. But most of them will involve things like the edges being relatively short and the vertices being well distributed across the screen. You know, you don't want to get all of the edges short by putting all the vertices on top of each other. That's cheating. So any way of formalizing what it means to have a nice picture of a graph you come up with will essentially tell you that lambda 2 has to be close to 0. Conversely, if you have a graph where lambda 2 is not close to 0, then you can say, there's no nice way of drawing it, or at least no particularly nice way of drawing it. You can find ways to cheat and get around that. So really, the threshold is somewhere when lambda 2 is, for me, about more than 10 over the square root of the number of vertices. That's when you don't get nice pictures, whether you do it this way or any other way. That said, I should say there are graphs for which there are nice pictures, but this technique does not produce them. That goes hand in hand as well. OK, so here's one of the other places that the Laplacian matrix comes up that is very important to me. It's when we're trying to do graph partitioning and graph clustering. So there are a number of reasons you may do this. By the way, when I say graph partitioning, I usually mean trying to divide the vertices of a graph up into pieces without too many edges crossing. Maybe you want to divide it in half with few edges crossing, or at least cut out some significant chunk without many edges crossing. I often want to do that because it's a way of doing divide and conquer. It allows me to divide a problem up and hopefully not have too much computation going between the different parts. I often also study this for the purpose of graph clustering. So often, say, if we're examining a social network graph, we want to find a cluster of vertices. That looks something like, usually I define as a number of vertices which have many more edges inside than edges going outside. So to that extent, I should define the boundary of a set of nodes. If I have a set of nodes in a graph, the boundary is the edges leaving that set, which hopefully you can see are sort of the bold edges going between S and the rest of the graph. So the Laplacian matrix enables us to measure boundaries. If you want to do that, take the characteristic vector of the set, the vector that's 1 at every vertex in the set and 0 outside, and take the Laplacian quadratic form in that characteristic vector. You'll see it's the sum of squares over all edges of the difference of the vector across the edge. So what this will give you is a value of 1 for every edge on the boundary. And for every edge that's not on the boundary, it'll either be the difference of 0 and 0 or the difference of 1 and 1. That'll be 0. So the Laplacian quadratic form enables you to measure the boundary exactly. So this is one of the motivations for one of the most popular spectral heuristics, which is for spectral partitioning. When people want to cut a graph into, say, 2 parts without too many edges crossing, one of the first things they try to do is they take a look at the second eigenvector, because that is a vector that's, say, not the all ones vector, but has a small Laplacian quadratic form. And if it has a small Laplacian quadratic form relative to, say, its norm, then presumably it should correspond to a cut with small boundary. Unfortunately, of course, the vector is usually not a 0, 1 vector. Usually it is real values. So what you do is you threshold it. It assigns some real number to every vertex on the graph, and you consider the level sets. So that would give me the set S in this picture. I think I took every vertex for which the eigenvector had value more than 0.75. You can also understand this in terms of the spectral graph drawing we were doing before. So this was the spectral drawing of that airfoil mesh. And really, if you do what spectral partitioning is doing, is it says, take a look at a set of vertices whose value in the second eigenvector are all less than some threshold. So the vertices are arranged, their x-coordinate along here corresponding to the second eigenvector. So it says, take a look at something like the left half of this picture. And that will be the set of vertices you will get from spectral partitioning. Now, that's a heuristic. You can also prove theorems about it if you want. So Cheeger's inequality says that this actually is a pretty good approximation of the best partition you could get. We just have to put a formula on what we really mean by the quality of a partition, which I'm not going to do for this talk, but you can look it up under Cheeger's inequality. Oh, and here's the partition this would have given us of the airfoil mesh when we actually lift it back to the original. So it's something that looks nice here as well. OK, now I think it's time to finally tell you what the entries are of the Laplacian matrix of a graph before we start working with it. So here I give you a graph, and here's its Laplacian matrix. So the Laplacian matrix has non-positive off-diagonals. For every single edge in the graph, there is a -1 in the off-diagonal. So the rows and columns of the matrix are indexed by the vertices. And so, for example, for that blue edge up there between node 2 and 6, that corresponds to this -1 in row 2 in column 6, and column 2 in row 6, because the Laplacian matrix is symmetric. There's zeros where there are no edges on the off-diagonal, and the diagonals are set to be the degrees of the nodes. In particular, the diagonals are set so the sum of the entries in every row is 0. So this is what's called a diagonally dominant matrix, which is a very well-studied family of matrices. It's called that because the diagonals are at least as big as the sum of the entries in every row and column, or in their row and column, I should say. And if you look at submatrices of Laplacians, which we often have to, they are also diagonally dominant. And algorithmically speaking, dealing with a Laplacian matrix or a submatrix or a diagonally dominant matrix are all equivalent problems. So sometimes I'll deal with something a little bit more general, but just talk about Laplacian matrices, because algorithmically we can reduce one to the other. Now, why don't I tell you how you would prove this? If you look at the Laplacian quadratic form, oh, by the way, I should have said, if we had a weighted graph, those off-diagonals should be the weights, not -1. Here we go. So when we take a look at the Laplacian quadratic form, again, it's the sum over edges of a square of differences across the edge. If you want, you break that term up by the edges into writing it as a sum of matrices, one for each edge. So for me, LAB is the Laplacian matrix corresponding just to edge AB. And you can take the Laplacian and write it as a sum of these. I mean, of course, there has to be one matrix. But if we, for edge AB, because you can imagine what happens if we don't have any of the other edges. And if you want to understand what does that elementary matrix look like for one edge, it looks like this. Say it only has 4 non-zero entries in it in the rows and columns indexed by A and B. So if A and B are 1 and 2, it's the matrix that's 1, -1, -1, 1. And you can see it if you multiply by x on either side, that gets you the square of x1 minus x2. But in general, of course, those matrices LAB would be padded with zeros. And then you would just have the 1s and -1s in the columns indexed by A and B. OK, so those are what Laplacian matrices look like. And now why don't I tell you a little bit about what we know about solving linear equations in them. OK, so a little over a decade ago, Xianghua Tang and I came up with a nearly linear time algorithm for solving the systems of linear equations in these Laplacian matrices. So what nearly linear time here means is the algorithm runs in time order m, where m is the number of non-zero entries in the matrix. That's what I'd like to be linear in, times some power of log n, c is some constant, and times a log of 1 over epsilon. Well, these are getting us epsilon approximate solutions. I'll tell you what that means in a moment. But at least think as long as your time is logarithmic in your notion of approximation, that's pretty good. Now, we used 2 main ingredients in this algorithm. One thing called low-stretch spanning trees, which I unfortunately don't have time to tell you about today. And the other is sparsification, which I will tell you about. But first, I should say that while this algorithm was nearly linear time in theory, asymptotically, in practice, it was not that useful, because that constant c was on the order of around 100. And log of anything to the 100 is not really anything you want to do. However, people kept improving these ingredients that we needed in the algorithm, improving low-start spanning trees, improving sparsification, until a few years ago, this constant c finally got down to 1. So Kudus, Miller, and Peng got us an algorithm where the running time is order m times log n times log 1 over epsilon. OK, there's a tilde over the big O. That is hiding a factor of log n. But that's very small. So I'll tell you, at this point, I thought we were done, because this is really asymptotically very fast. But I was wrong. So Cohen, King, Pachuki, Peng, and Rao got that constant down to 1/2. Now, to appreciate a running time like m log m to the 1/2, think about this. If you only want a constant factor accurate solution, if epsilon is a constant, and I will actually tell you that in most applications we care about, epsilon will be a constant, like a 1/10. This is asymptotically faster than sorting the non-zero entries in your matrix. Sorting would be something like m log n. And this is part of why, if I can fit a Laplacian matrix in the memory of my computer, I no longer hesitate to solve systems of linear equations in it. Like sorting, I now understand is something we can do very quickly. And there is some pretty good code for this. I usually point people to the Lean Algebraic Multigrid by Livna and Brandt, or the Combinatorial Multigrid by Kudus. OK, neither of those are implementing these algorithms. They're both developed beforehand. But you can think of these analyses, if you like, as justification for why algorithms like these should work. And there's some others I'll tell you about in a moment. OK, so now I should tell you what it means to get an epsilon accurate solution, because if any of you are going to follow up or use any of this, this is something that's very important to know. So we say that a vector x tilde is an epsilon approximate solution to a system of equations, like ax or lx equals b, if we want the norm of x tilde minus x to be small. We want the vector to be close, that we compute to be close to the correct vector. For how close? Well, it should be less than epsilon times the norm of the solution. That's sort of the right notion of relative accuracy. And the one thing that's going to seem a little confusing here is the norm that I'm using is not the standard Euclidean norm. I'm measuring error in the matrix norm. So that is, you see this norm has a little LG underneath it. And to understand the difference, usually the norm of a vector, we could say, is the square root of v transpose v. Here you just put the matrix in the middle. Now, you might wonder, why am I measuring the error in this funny matrix norm? And I at first wondered it myself, too. But when I started reading papers in numerical linear algebra, this was the way, sort of guarantees that we usually got from the algorithms in the field. And people are not doing this just to be difficult. So it turns out this is the way you want to measure the error. By which I mean, if you are taking an algorithm for solving systems of linear equations and using it as a subroutine in some other algorithm, in every single case that I know of, the way you want to measure the error in order for it to play nicely with the algorithm that's calling it is to measure the error in this matrix norm. So it's a little bit of complication up front. But this is why I say we can essentially always get away with epsilon being a constant in most of the applications that I know of. Solving to constant accuracy in this norm suffices. And if it's not constant accuracy, still, this is the sort of norm that you will usually want to measure the error in. For example, let's say we were trying to compute the eigenvectors corresponding to the smallest eigenvalues of the Laplacian. You would do that by using the power method or the Lanczos method, but on the inverse of the matrix, where you don't really want to construct the inverse. You want to do it by solving systems of linear equations. And if you look at the error analysis, this is the right norm in which to measure the error to see that you can quickly compute those eigenvectors, and therefore do all of that spectral graph theory algorithmically very quickly. OK, so now that we know we can solve systems of linear equations and Laplacian matrices quickly, it occurs to us that we can use this as a subroutine in other algorithms. And I want to tell you about one of my favorite examples of doing this. This is in linear programming. So there are a lot of linear programming problems that are naturally defined on graphs. And there are a number of ways of solving linear programming problems, but one of the most powerful is the interior point methods. OK, so this is a good point where I should ask, how many of you have seen interior point methods before? Wonderful. That's about half. So OK, so for those who haven't, interior point methods are ways of solving linear programming problems. And if you open up the black box of what an interior point method is doing, what you will see is that it's solving a sequence of systems of linear equations. It's basically taking something like a linear program, smoothing it out into something, and then solving it by Newton's method. And every iteration of Newton's method, you need to solve a system of linear equations. And it turns out that if you have a nice family of linear programming problems, you get a nice family of systems of linear equations that you need to solve. So some examples, say, are maximum flow and minimum cost flow, some of the classic optimization linear programming problems. The fastest algorithms we have, at least asymptotically for solving those, now go through this route. When you run an interior point method, basically, you discover what you need to do is solve systems of linear equations in Laplacian matrices. And actually, so the result of Madri now gets us the fastest algorithm for these problems by also giving us a sort of souped-up, faster interior point method than the classical ones. There are other problems now, like shortest paths. OK, shortest paths in graph we think of as an easy problem, unless they're negative length edges. OK, probably there shouldn't be. But if you have both positive and negative length edges and you want to compute shortest paths, the asymptotically fastest algorithms we know for doing that now go through interior point methods that then use Laplacian linear equation solvers. Another one I mentioned is isotonic regression is a classic problem from statistics. I think that's the easiest one to understand. And the one I mentioned at the bottom is called Lipschitz learning. It is a variation on this problem of interpolation on graphs that I mentioned at the beginning. That it is very easy to account for error, both in the labels and, say, in the network. And if you want to do regularization to account for noise in, say, the lengths of edges in your network, again, it turns into a linear programming or semi-definite programming problem that we can solve by interior point methods by doing this. So to give you one example of this, let me explain what's going on with maximum flow. So again, the maximum flow problem, you're given a directed graph usually, and two particular nodes, a source, S, and a sink, T. And you're given some capacity of how much you can flow on every edge. And then your goal in this problem is to send as much stuff from S to T as possible, subject to a few constraints. So I described this as maximizing the flow out of S. That will be equal to the flow into T, because we have this other lossless condition that says for every single vertex other than S or T, the amount that flows into it is equal to the amount that flows out. OK, that's a flow. And then we have these linear conditions that on every single edge, the flow on every edge AB should be between 0, should be non-negative, and at most the capacity of that edge. So here I've drawn the capacities of these edges. And the maximum flow in this case looks like this. So we have 2 over that edge, 1 over some of those edges. And this is the maximum flow value 3 in this graph. So when you run an interior point method on this maximum flow problem, what you will discover is you're solving a number of systems of linear equations. I guess I didn't write this as a system, but what it looks like is this. It corresponds to an electrical flow problem. We want to solve a problem with maximizing the flow out of the source S. Well, sort of the electrical flows that I showed you before are also flows. So they also have the property that for every intermediate vertex, the flow in should be equal to the flow out. The main difference is the constraint. The constraint is now a sum of squares constraint. So as opposed to having the flow on every edge be between 0 and its capacity, you have some weighted sum of squares of the flows over edges, and that should be at most some number C. And actually, when you maximize that, you will get equality there. It won't be an inequality when we actually compute the maximum flow. And what happens, what's changing in each iteration is the weights are changing. So when you run an interior point method to solve this, the graph will be the same, but at every single call, you will get different weights. And you'll have to solve a system of equations, basically same network, different weights. You do that a couple of times, you wind up solving the maximum flow problem. That's what an interior point method is doing. One of the things I should point out that's a little mysterious about it is the maximum flow problem has this directed graph and a non-negativity constraint on the flows, and some capacity constraints. And once you turn this into a system of linear equations, those conditions go away. The non-negativity condition is not there anymore. But you're solving the maximum flow problem anyway. So one way of understanding this, if you like, is you had some sort of network of resistors if you treat your graph as a network of resistors, you can imagine what you do is you compute the electrical flow. And now take a look and see, have you violated some of the conditions you want? Like, are you flowing too much current on some edge? Or are you flowing negative on some edge? If you are, increase the resistance on those edges. That will decrease how much those edges are being used. And then if you do that iteratively, you actually eventually wind up getting the maximum flow. But interior point methods, I should say, are doing this in a particularly intelligent way. OK, so now I want to tell you about sparsification. So the takeaway from this is that every single graph can be approximated by a sparse graph. And by that, by approximation, I mean the Laplacian matrices should be similar. So here's my notion of similarity. I will say that one graph is an epsilon approximation of another, or their Laplacian matrices are epsilon approximations of another, if for all vectors x, the quadratic forms should be very similar in ratio. Meaning, I want to say G is an approximation of H if for all vectors x, the value of the quadratic form in G divided by the value of the quadratic form in H, or the other way around, is between 1 over 1 plus epsilon and 1 plus epsilon. And when that condition holds, I will say that the Laplacian matrix of H, I'll write this with a tilde of epsilon, is an epsilon approximation of the Laplacian matrix of G. So to see what this sort of approximation gets you, first remember that the Laplacian quadratic form measures boundaries. So this means that when I do this approximation, the boundary of every single set of vertices in H and G has to be approximately similar. OK, now I told you I'm going to sparsify graphs, which means I'm going to reduce the number of edges. When I reduce the number of edges, I'm going to increase their weights. Think of it as a conservation of mass phenomenon. You have to really preserve the sum of the weights of the edges in order to get an approximation. So I'll just sort of think of it as making some of them thicker. But this does tell you that for every single set of vertices, if G and H approximate each other, the size of the boundaries of G and H have to be approximately the same in the original and in the approximation. It also turns out that when you have an approximation like this, systems of linear equations are similar. Formally speaking, if LH is an epsilon approximation of LG, then the same is true of their inverses. Or because these are singular matrices, the same is true of their pseudo-inverses. And that's an easy exercise in linear algebra. So this is one of the reasons I was very interested in it, because it means that if I want to solve systems of linear equations, it suffices to think about solving systems of linear equations in sparse matrices once I can do the sparsification. And you would think that that would take less work. It also tells you that things like effective resistances are similar. And eigenvalues are similar. And to the extent eigenvalues are isolated, eigenvectors are similar. OK, so how do we get sparsifiers? Let me begin by considering sparsifiers of the complete graph. That is the graph with all edges. OK, we know how to sparsify the complete graph. That's not very hard. The graphs that give us sparsifiers of the complete graph are the good expander graphs. So many of you will have encountered expander graphs because they give us good low-density parity check codes. But they come up in a lot of other places, too. So we say a graph is an expander graph if every set of vertices has unusually large boundary for the set size. Sort of what's unusually large, usually we want something like the boundary for every set should be a constant multiple of the number of vertices in the set. This is really equivalent to saying that lambda 2 should be large. If you have actually a D-regular graph, lambda 2 should be close to D. Actually, all of the eigenvalues should be close to D is a good spectral way of defining what it means for a graph to be a good expander. OK, so the expanders give us very good approximations of the complete graph. This is my picture, my cartoon that demonstrates it. The graph on your left, right, is the complete graph on 10 vertices. How many of you recognize the graph on the right? Oh, good. It's the Partition graph. For those who aren't sure, I'm told that Paul Erdős once said that if he were stranded on a desert island and could only have one graph, it would be the Partition graph. It has a lot of nice properties. In this case, the eigenvalues are very close, and I drew the edges thicker because every edge there should have weight 3. Because in the complete graph on 10 vertices, every edge has weight 1, and every node then has degree 9. So here, I should have in the Partition graph, every node has degree 3, but then I want 3 edges of weight 3, and that'll get us weighted degree 9 at every vertex. OK, more generally, you can take a random regular graph. Random regular graphs are almost always expander graphs, and those will give you very good approximations of the complete graph. So if we want to do it for more general graphs, there is also a way of getting approximations by random sampling. So the idea is we are going to assign some probability, PAB, to every single edge. We're going to choose them carefully. I'll tell you how in a moment. And then the way we sparsify is after choosing these probabilities, we include each edge in our approximation with probability PAB. If we do include an edge, we increase its weight by dividing by PAB. So the point is we're sort of downsampling. We choose edges with probability PAB, but when we include them, we greatly increase their weight. This means that each edge we include at least an expectation with its original weight. If I use a sampling scheme like this, then the expected Laplacian matrix I get of my approximation will be the sum over all edges, and I can write the Laplacian matrices for those edges. I only include that edge with probability PAB, but when I do, I include it with weight, its original weight, divided by PAB. So those two PAB terms cancel. So if I do a sampling scheme like this, at least in expectation, I get the right matrix. Then what you need to do is you need to prove some concentration result to prove that you get something that's very close to the original Laplacian. And the right way to do this is by choosing edges with probability proportional to their weight times the effective resistance between their endpoints. And if you do that, that gets you a very good sparse approximation. One way of seeing that, for those who are used to, say, concentration bounds for random matrices, either by Schweid-Winter or the recent theorems of Trop, this choice of sampling probabilities optimizes the application of those theorems. It optimizes the variance, minimizes the variance terms within those. And if you do that, you see you can get a sparse approximation of any graph using only order n log n over epsilon squared edges, where epsilon is your degree of approximation and n was the number of vertices. OK, so that's pretty sparse. We can get sparser. You can get rid of the log n. So the best graph sparsifications we know right now, we think it might be optimal, but we're not sure, is that for every graph on n vertices, no matter how many edges you start with, there is an epsilon approximation with essentially 4 times n over epsilon squared edges. So for those who know about expander graphs, which I told you are the best approximations of complete graphs, the best expander graphs are the Ramanujan expanders. And these approximate every graph within a factor of 2 of how well the Ramanujan graphs approximate the complete graphs. So they're at least pretty close to optimal, but we suspect they actually are. OK, so now to wrap up, I want to tell you about this very recent algorithm of King and Sachdeva for solving systems of linear equations in Laplacian matrices. To begin, I will just remind you a little bit about how Gaussian elimination works. And I hope you will humor me, because they take a different perspective on it than, say, the one I was taught. OK, so to begin, when you want to solve a system of linear equations by Gaussian elimination, you see, if you have a symmetric matrix, you're essentially using Gaussian elimination to write the matrix in the form U transpose U, where U is an upper triangular matrix. OK, people usually write LL transpose, where L is lower triangular, but in this lecture, L is a Laplacian. So we'll write U transpose U. What they're going to do is they're going to do approximate Gaussian elimination. They're going to take the Laplacian and approximate it by U transpose U, and their U's are always going to be sparse. And I should remind you that once you have a representation of a Laplacian like this, you can solve systems of equations in it quickly, because you can solve systems of equations in an upper triangular or lower triangular matrix in linear time. That's just a forward solve or backward solve. OK, so I told you that they're going to think about Gaussian elimination a little bit differently than we usually do. So let's say this is the matrix we want to do Gaussian elimination on. What they're going to do is find the rank 1 matrix that agrees with this matrix on the first row and column. So here's the first row and column, and here's the rank 1 matrix that agrees with it in the first row and column. And you can see that it's rank 1 because I've written it as an outer product of a vector with itself. Then what you do is you take that rank 1 matrix, you subtract it, and now you have eliminated the first variable. You have a matrix that's 0 in the first row and column. And what do you do with that matrix? Well, you find the rank 1 matrix that agrees on the next row and column. And of course, it should be 0 at the top. I've written this again as an outer product, so you can see it's a rank 1 matrix, and we subtract that. And you keep going. So this is the way they understand Gaussian elimination, as successively subtracting off sequences of rank 1 matrices. And when you're done with this, you will have taken your original matrix and written it as a sum of outer products of vectors with themselves, with increasing numbers of zeros in each of those vectors. So this is exactly the same thing as Gaussian elimination that you were usually taught, but a somewhat different perspective that plays better with the theorems of random matrix theory. Because a lot of the theorems of random matrix theory apply very naturally when we are adding matrices together. In adding random matrices, usually when you write Gaussian elimination in terms of products and operations, and you have products, and that's harder for random matrix theory. The thing I need to point about, where's all the time in Gaussian elimination? It's the time to do these subtractions. So that takes time proportional to the sum of the squares of the non-zero entries in these vectors. So if we're going to make this fast, we want to make all of those vectors sparse. And that doesn't necessarily happen when you're doing Gaussian elimination. Actually, the only way it will really happen now is we're going to do some sort of random sampling on them that we can do for Laplacians. Okay, finally, so that to get your U transpose U, you take all of these vectors, you concatenate them together into 2 matrices. This is 1 matrix times its transpose. OK, I'll write it as U transpose U. So that's what Gaussian elimination is doing. So what they're going to do to make this fast is use a special property of elimination in Laplacians, which is that if I start out with a Laplacian matrix and I do an elimination operation on it, I get another Laplacian matrix. OK, that is a very useful and very special closure property. And graphically, you can understand this. What happens when I'm eliminating a vertex, say vertex 1 there, is I wind up removing it from the graph, and in the submatrix, I add a clique between its neighbors. It's actually a weighted clique. And there are weights depending on the weights with which edges were attached to the node that I eliminated. But you wind up adding the weighted clique. That's what Gaussian elimination does. And what King and Sachdeva suggest doing is they say, OK, every time you're going to add that clique, sparsify it. Not only that, they sparsify it before they even construct it. So they don't have to build it. You can implicitly sparsify it and figure out what a good sparsifier of it is. And let's say it's by a very, very simple random sampling rule. I won't tell you exactly the rule because I'm running out of time. But basically, I'll tell you that every time you eliminate a node of degree d, if it has d edges, it'll have d neighbors, and then you wind up sparsifying it by adding in a graph with exactly d edges. So throughout the process, the number of edges in the graph basically remains the same, but the number of vertices goes down. And when all is said and done, this gets you an algorithm that takes time order m log cubed n. Log cubed is not that fast, but if you're willing to sacrifice a little bit of the simplicity, you can make it faster. And it is very, very, very simple and clean, which also makes me hopeful that we can apply it to other families of systems of linear equations. Well, we know we can for a few others. And if any of you ever took a course in numerical linear algebra, this looks a lot like using incomplete Cholesky factorization preconditioners, but probably is the right way to do it. And those are one of the heuristics that are very useful for solving systems of linear equations and Laplacian matrices. And people have been studying those for a long time. OK, so let me not tell you how we analyze it, other than we use sort of a matrix martingale, or concentration inequality. Let me finish by telling you about where this is going. So there have been some interesting recent developments in this business. So for the last decade, we've been studying Laplacian matrices. We finally know how to solve some richer families of systems of equations. One of my favorite are when we have complex weights on the off-diagonal. So we no longer need to have just, say, -1s on the off-diagonals. As long as you have a Hermitian matrix, you can have roots of unity on the off-diagonals. Another system we can solve is a system that people call the connection Laplacians. I encountered these in the work of Amit Singer on cryo-electron microscopy, and they come up in a lot of computer vision problems. These actually are block matrices, so rather than having one real number associated with every vertex, you have a vector associated with every vertex. And instead, every single edge has a little 2x2 block matrix like that, where there are identities on the diagonal and orthonormal matrices on the off-diagonals. We can now extend techniques like these approximate Gaussian eliminations to solve systems of equations in those as well. So also, I should mention, over the last year, my group and some other colleagues who are interested in this have been doing a lot of work on implementing a lot of the ideas related to this machinery, because it finally seemed ripe to do it. So there's a Julia package now for those who code in Julia called Laplacians.jl that ties together these linear equation solvers with algorithms for solving linear programming problems and computing sparsifiers and those sorts of spanning trees. And if you want to play with these sort of techniques, this is a good package, I think, to do it with for now. And it's open source, so you're also welcome to contribute. So finally, if you want to learn more about all of this, there are a few things I will recommend. So I have a web page that I maintain with a complicated and long name, something like linear equation sparsification, local graph clustering, and so on, everything related to this talk. It's near the top of my webpage, and that will point you to survey papers and all of the papers that contain from which the content of this talk is drawn. We also, I also teach courses on a lot of this material, and for those courses, there are lecture notes. So if you want to see a nice introduction to this stuff, you can look at my courses on graphs and networks or spectral graph theory. And finally, there's a very, very nice monograph by Nishith Vishnoi that I recommend called LX equals B. Thank you.
I'm going to come to the stage.
Okay.
To ask you the question.
Sure.
Okay, so you all have in your program, you have a graph on the cover of the program. And here you also have a graph. Okay? Mm-hmm. Now, how do these graphs come about? Antoni Gaudí came up with this technique, which is called trencadís. And what this is you take a solid body, and then he approximates the solid body with flat surfaces. Okay, this is how all this is constructed. So my question is, if you have a good approximation like this to a solid body, so you have a graph like that, should you be able to tell by the Laplacian that that is indeed a good approximation to a solid body? And conversely, if you have a solid body and you want to approximate it this way, can you get like how these eigenvalues behave with the approximation, with the fineness of the approximation?
Okay, so the answer to this question is yes, for many reasons. So first, what I didn't tell you when I mentioned that paper by Drew Garamani and Lafferty about interpolation on graphs that I began with. So that was a paper actually that motivated by the manifold hypothesis, this assumption that a lot of real-world data actually lives close to some smooth, low-dimensional manifold. And the reason that they were doing this interpolation on Laplacians was because they were trying to do semi-supervised learning and learn functions actually on these manifolds. And therefore, they were interested in approximating these manifolds by discrete structures like you suggest. OK, so that motivated a huge amount of work afterward on understanding when you take a manifold and when you discretize it, how well are you approximating it? And if you take, say, the Laplacian on the discretization, which are the right edge weights to approximate the Laplacian operator on the manifold or the Fokker-Planck operator on the manifold. There is another literature that also studies this, which is people using the finite element method to solve systems of differential equations, which precedes it by many, many decades. And I have never actually seen anyone connect these two literatures in a nice way, and I would love to. So in that case, let me ask you a question. There are so many planar graphs for which this spectral method that I showed you originally gives you beautiful pictures of them, often planar embeddings of the graphs, although not always. And for the last 20 years, I've been trying to find a theorem to go along with this empirical observation, and I have not been able to. I suspect that the technology to do it somewhere lies within the differential equations community. But because people do know that when you take say, nice approximation. Like even, a good theorem would be if you take a good discretization of a planar region and then take a look at the eigenvectors, that you're actually getting a planar embedding. But I still haven't seen a theorem that gets us to that yet. But
if you're looking for a good name for such graphs that are good approximations, I would suggest Gaudi graphs.
Yes. Thank you.
Since I'm here, let me make a couple of announcements. The awards lunch is going to take place in this space. Starting at 1:30, it's going to be a stand-up tapas-like lunch. And also another thing that these classrooms, it's not very easy. If there are unoccupied seats, it's not very easy for people to jump over. So try to not leave empty spaces next to you when you sit. That's all. I guess any other questions? Well, thanks again for a beautiful lecture.
Thank you.